Hi, everyone, and welcome to this session on building the future web with modern JavaScript. This is Sathya. My name is Mathias. We work on the V8 team at Google. And V8 is the JavaScript engine that's used in Google Chrome and in other embedders such as Node.js and Electron, for example.
JavaScript started out as the scripting language of the web. And to this day, it's still a crucial piece of web technology. But today, JavaScript's reach extends far beyond the web to the entire surrounding platform.
So if we take a step back from just V8 and Chrome, we can see that JavaScript allows you to build engaging web experiences that work in a wide variety of browsers. And with Node.js, JavaScript can be used to build powerful command line tools, servers, and other applications. React Native enables building cross-platform mobile apps also using JavaScript. With Electron, JavaScript and other web technologies can be used to build cross-platform desktop apps. JavaScript can even run on low-cost IoT devices nowadays.
JavaScript is everywhere. As a developer, learning JavaScript or improving your JavaScript skills is an excellent time investment.
At Google, we want to enable this enormous JavaScript ecosystem. And we do so in multiple ways. First, there's TC39. This is the committee that governs the evolution of ECMAScript, which is the standard behind the JavaScript language. We actively participate in these standardization efforts together with other browser vendors and industry stakeholders, and we bring back feedback from us as implementers and from you, the developer community.
On top of our participation in the standards process, we constantly improve our own JavaScript engine, V8. We boost its runtime performance, reduce its memory usage, and implement new language features as they're being standardized.
The V8 project's mission is to lead real-world performance for modern JavaScript and to enable developers to build a faster future web. Now, that's quite a mouthful. That's a lot of words. But don't worry, because in this presentation, we're going to zoom in on some aspects of this mission. First, let's discuss what we mean when we say real-world performance. We've stepped away from synthetic benchmarks that we used in the past. Instead, we now focus on optimizing real websites and JavaScript applications. Of course, we need a way to measure our efforts in this area. And luckily, some modern benchmarks are good approximations of real-world performance. We consider the Speedometer 2 benchmark to be a good example of that. It is a good proxy for real-world performance because it uses common frameworks, libraries, and build tooling patterns that are being used on production websites that we see in the wild. And over a time span of just 4 Chrome releases, we achieved a 21% overall improvement on Speedometer 2. And one key highlight here is that we more than doubled our runtime performance of the React framework. That's a pretty big deal. And this is not just optimization in isolation. Our data shows that optimizations to apps in Speedometer 2 translates to performance improvements in real-world apps. Now, Speedometer focuses on web apps quite heavily. But if you think about it, a lot of web development tooling is built on top of Node.js. And performance matters there as well. So we decided to optimize for popular real-world tools, such as TypeScript, Babel, and Prettier, as well as the outputs that they generate, by using the web tooling benchmark. And we've had some nice improvements so far. New features are being added to the JavaScript language constantly. We're working on making them available in V8 and Chrome as soon as possible. Modern JavaScript features have good baseline performance, and we're continuously working on making them even faster. So as a developer, please don't hesitate to use these modern JavaScript features. They're often more performant than handwritten alternatives. So it means that you can just focus on writing idiomatic code that makes sense for you, and we'll worry about making it fast.
On top of runtime performance, we're constantly focusing on reducing V8's memory footprint and improving developer tooling for debugging memory leaks. This is especially important for low-power devices, such as mobile phones or even IoT devices. Recently, by changing V8, we made it easier to find detached DOM trees or leaks in event listeners using the Chrome DevTools. Better memory tooling ties directly into our mission, as it helps developers build better apps. Well, we talked about real-world performance. We talked about tooling. I think we skipped the middle part of our mission. Yes, it's modern JavaScript. For the rest of this talk, we're going to be taking a look at some of the cutting-edge JavaScript language features that we've been working on, both on the standardization side and on the implementation side in V8.
Let's start off with ECMAScript modules. Modules are a major new feature and actually a collection of features in JavaScript. You may have used a user-land JavaScript module system in the past. Maybe you used CommonJS in Node, or maybe you used AMD, or maybe something else. But one thing all these module systems have in common is that they allow you to import and export values. And JavaScript now has standardized syntax for exactly that. Within a module, you can use the export keyword to export just about anything. You can export a const or a function or any kind of value. All you have to do is prefix the variable statement or the declaration with the export keyword, and that's it. You're all set. Now you can use the import keyword to import the module from another module. So here we're importing the repeat and shout functionality from the lib module, and we're using it in our main module. Modules are a little bit different than regular scripts. For example, modules have strict mode enabled by default. Also, this new static import and export syntax is only available in modules. It doesn't work in regular scripts. And because of these differences, the same JavaScript code might behave differently when treated as a module versus a regular script. As such, the JavaScript runtime needs to know which scripts are modules. On the web, you can tell the browser that a script is a module by setting the type attribute to module. Browsers that understand type module also understand the noModule attribute, and they ignore scripts with the noModule attribute. This means that you can serve a module tree to module-supporting browsers while still providing a fallback for other browsers. And the ability to make this distinction is pretty amazing by itself, if only for performance. Just think about it. Only modern browsers support modules. That means if a browser understands your module code, it also supports features that were around before modules, such as arrow functions, for example. So you don't have to transpile those features in your module bundle anymore. You can serve smaller and largely untranspiled bundles using modules to modern browsers, and only legacy browsers need that noModule payload. Now you can optimize delivery of your modules even further by using link-rel module preload. This way, browsers can preload and even pre-parse and pre-compile modules and their dependencies. Now, you may have noticed that we're using the MJS file extension for modules. On the web, the file extension doesn't really matter, as long as the file is served with a JavaScript MIME type, which is text/JavaScript. The browser already knows that it's a module because of the type attribute that you put on the script element. But still, we recommend to use MJS for modules for consistency with Node.js, where MJS is actually required. Node has experimental module support for files, but only with the MJS extension. The Node.js team is still working out some issues around interoperability here, so expect more updates on this soon. We recommend to use the JS extension for regular scripts and the MJS extension for modules. Node.js needs it to make modules work, and on the web, the file extension doesn't matter anyway, so you might as well be consistent with Node and use MJS. That way, you can potentially run the exact same modules, the exact same files, both on the web and in Node.js. So far, we've only used static import. With static import, your entire module graph needs to be downloaded and executed before your main code can run. Sometimes, you don't want to load a module up front, but rather on demand, only when you really need it, when the user clicks a link or a button, for example. This improves the initial load time performance. Well, we recently added support for dynamic import, which also works in regular scripts, unlike static import. So let's say you have some navigation links in an HTML element, in an HTML document, rather. And when the user clicks or taps on them, instead of navigating to another page, you want to download a module and run some code for it, which instantiates the module and then updates the page. We can do that as follows. We add click event listeners to the links that cancel the navigation, and then dynamically import the corresponding module as specified through the data entry module attribute. Once the module is loaded, we can use whatever it exports. In this case, we use the load page into export, which is a function that is called, and then it instantiates the module, and it updates the page. Another new module-related feature is import.meta, which gives you metadata about the current module. The exact metadata you get is not specified as part of the standard. It depends on the host environment. This means that in a browser, you might get different metadata than in Node.js, for example. Here's an example of import.meta on the web. By default, images are loaded relative to the current URL in HTML documents. But import.meta.url makes it possible to load an image relative to the current module instead. It gives you much more freedom. With modules, it becomes possible to develop websites without using bundlers such as Rollup or Webpack. However, loading performance of bundled applications is better than unbundled ones. And one reason for this is that the import and export syntax is statically analyzable, which means it can help these bundler tools to optimize your code by eliminating unused exports. Static import and export are more than just syntax. They are a critical tooling feature. Of course, we're working to improve the performance of native modules out of the box, but please continue to use bundlers before deploying to production. It's very similar to minifying your code before deploying. That's always going to result in a performance benefit because you end up shipping less code. And bundling has the same effect. So keep bundling. All modern browsers already support modules as of this morning when Firefox 60 was released. As we discussed, Node.js has an experimental implementation behind the flag.
Well, that was a lot of cool features involving modules. Now let's take a look at some of the smaller, more incremental features coming to JavaScript. Let's start off with a little quiz. Quick, what's this number? Is this a billion? 10 billion? What about this number? What's the order of magnitude for this number? I'm sure you can all answer this given enough time. But large numeric literals are difficult for the human eye to parse quickly, especially when there are lots of repeating digits, like in the first example. That's why a new JavaScript feature enables underscores as separators in numeric literals. So instead of writing these like this, you can now write them like this, grouping the digits per 1,000. Now it's easier to tell that the first number is, in fact, a trillion, and the second number is in the order of a billion. This small feature helps improve readability. And it's not just for numeric literals of base 10. For binary numeric literals, you may want to group the bits by octet or by nibble, depending on the use case. For hexadecimal numeric literals, you may want to group the digits per byte. This feature is so cutting edge that it's not shipping anywhere yet. It's still being standardized, and there's some open spec issues that need to be resolved. We have an implementation behind a flag in Chrome and V8. And as soon as the spec is ready, we will update our implementation and ship it.
Another new feature involving numbers is BigInt, which brings arbitrary precision integer support to JavaScript. Let's take a look at what that means exactly. Numbers in JavaScript are represented as double precision floats. This means that they have limited precision. The max safe integer constant gives the greatest possible integer value that can safely be incremented. And you can see that here. If we increment it once, we still get the correct result. But if we then increment it a second time, we get the same number as before. That's not the right result, mathematically speaking. And this happens because the result is no longer exactly representable as a JavaScript number. BigInts are a new numeric primitive in JavaScript that can represent integers with arbitrary precision. With BigInts, you can safely store and operate on large integers even beyond the safe integer limit for regular numbers. To create a BigInt, just add the n suffix to any integer literal. The global BigInt function can be used to convert a number into a BigInt dynamically. And here, we're combining those two techniques to calculate the sum. And this time, we do get the correct result. Here's another example. We're multiplying two regular numbers. And if we take a look at the least significant digits here, 9 and 3, we know that the result of the multiplication should end in 7, because 9 times 3 is 27. However, the result ends in a bunch of zeros. That can be right. So let's try this again with biggins instead. And indeed, this time, we do get the correct result. Biggins make it possible to accurately perform integer arithmetic. And most importantly, it's now possible to safely represent a Google in JavaScript. This is going to help me in my day-to-day programming for sure. On a more serious note, why would you need biggins? Arithmetic on large numbers is one use case, but what else is there? Well, it turns out that without biggins, it's very easy to run into bugs that are very hard to debug. Tweet IDs, for example, are 64-bit integers, meaning they cannot safely be represented as a JavaScript number. So if you tried, you would run into very sneaky bugs where some IDs would suddenly turn into other numbers. And until now, developers had to represent such IDs as strings instead. But with biggins, you can represent them using a numerical type when it makes sense to do so. Here's another example of a real-world bug that occurs in Node.js. Sometimes different files or folders appear to have the same inode, which is supposed to be a unique number per file. The fundamental cause of this bug is the imprecision of JavaScript numbers. Biggins don't have this problem. Another use case is representing high-precision timestamps accurately. Using regular numbers, this is not possible without losing accuracy. But with biggins, the precision is guaranteed. That's why Node.js is currently looking into exposing biggins instead of numbers for some of its built-in APIs where it makes sense. Historically, developers have been working around the lack of precision by using bignum libraries implemented in JavaScript. And when we benchmarked our native biggin implementation, we found that it consistently outperforms user-lent alternatives. So once biggins become widely available, applications will be able to drop these runtime dependencies in favor of native biggins. This will help reduce load time, parse time, compile time, and on top of all that, it will offer significant runtime performance improvements. I can't wait for that to happen. But right now, it's still early days for biggins. Chrome 67 ships with biggin support. This means that Chromium-based browsers, such as Opera, support it as well. But other browsers are still actively working on their implementations. You can expect wider biggin support soon.
You may be familiar with for-off loops and the iteration protocol. And more recently, JavaScript gained support for async functions. A new set of features combines these together to form async iterators and generators. Let's say you want to find out the response size of a request. Currently, async functions make it easy to work with the fetch API and the response stream. But there's still a bit of boilerplate required to iterate each chunk, await each chunk, and then manually check if we're done with the stream. With async iterators, the code is much cleaner and more ergonomic. There's no manual awaiting of each chunk or checking to see if the stream is done. The for await of loop just does all that. Streams aren't async iterable quite yet, but there's ongoing standardization work being done to make it work. Similarly, you can expect more and more APIs to add async iteration support in the future. And this is already happening in Node. So Node.js has built-in streaming APIs, such as readable stream, that can be used with the old-school callback style. In this example, we're collecting all data chunks until the stream ends, at which point we print the result. To do so, we need two different callbacks. With Node.js version 10 now, you can use async iterators out of the box. So instead of using callbacks, we can now write a single for await of loop to iterate over all the chunks. Browser support for async iterators and generators, including the for await of syntax, is pretty good already. Chrome, Firefox, Opera, and Safari Tech Preview already have support, as does Node.js. For other browsers, Babel is your friend. It supports transpiling the for await of syntax.
Regular expressions also recently got some much-needed love, with multiple new features that help improve their readability and their maintainability. And one such feature is called .all mode. Let's say you have some input text, and you want to apply a regular expression to it. In this case, we can see that the text contains the phrase "hello world" right there. So let's write a regular expression that checks whether the input contains hello followed by any character followed by world. In regular expressions, the dot can be used to match arbitrary characters. So this regular expression should match, right? Well, it turns out that it doesn't match. The problem is that the dot, in fact, does not match all characters. It only matches characters that JavaScript does not consider to be line terminators. And there happens to be a line terminator in the input string right there. That's a new line. Sometimes you really do want to match any character, including new lines. This problem is so common that developers have started to use workarounds like this. So here, we're matching any whitespace character or any non-whitespace character, which effectively matches any character. Another workaround is to use a negated empty character class. This matches any character that is not nothing, which effectively matches any character. So these two techniques work, but they're not very intuitive or readable. And stuff like this is why regular expressions get a bad reputation for being hard to decipher. But it doesn't have to be this way. A new regular expression flag makes the dot truly match any character, including line terminators. You can use this as flag to enable the .all mode. This is one of those flags that you'll probably want to enable for every single regular expression you write from now on, just like the U flag for Unicode mode. These two flags make the behavior of JavaScript regular expressions less confusing and more sensible. And here's an easy trick to remember these flags. Instead of SU, you can just write US. This makes your code more America-friendly and your regular expression behavior less surprising. .all mode is currently supported in Chrome, Opera, Safari, and Node.js. But Babel can transpile this feature, so you can use this while still supporting other browsers as well.
Another new feature improves capture groups in regular expressions. Let's take a look at an example. This regular expression matches 4 digits followed by a hyphen, followed by 2 digits, followed by a hyphen, followed by another 2 digits. Each set of digits is wrapped in a parenthesis to create a capture group. Each capture group in a regular expression automatically gets an index and can be referenced using that index. There are 3 capture groups in this example. So the first one maps to index 1 in the match object. The second capture group maps to index 2. And the third capture group maps to index 3. You get the idea. Capture groups are useful, but referencing them by index is not very readable or maintainable. Imagine adding a new capture group to the start of the pattern. Then all the existing indexes shift, and all the code relying on the ordering has to be updated. A new feature makes it possible to assign a name to each capture group. So this makes the regular expression itself more readable because it clarifies what each group stands for. Instead of using indexing, we can now refer to each capture group by name. So this improves the readability and maintainability of any code that uses the regular expression as well. So now we can refer to the first capture group with the identifier year, second capture group with the identifier month, and the third capture group with the identifier day. Named capture groups are currently supported in Chrome, Opera, Safari, and Node.js. For wider browser support, we recommend using Babel to transpile and polyfill this feature.
Another regular expression feature involves Unicode properties. The Unicode standard assigns various properties and property values to every symbol you can think of. Unicode property escapes make it possible to access these Unicode character properties natively in regular expressions. For example, the pattern script extensions Greek matches every symbol that is used in the Greek script. Previously, we had to resort to large runtime dependencies or build scripts to just mimic this functionality. but those solutions led to performance and maintainability issues. But with built-in support for Unicode property escapes, creating regular expressions based on Unicode properties couldn't be easier. And this is not just useful for complex Unicode-specific properties. It also helps with some more common tasks, such as matching ASCII characters, for example. You could just spell out the ASCII range from code point 0 to 7F yourself, but why would you bother when you can just refer to it by name like this? It's easier, and your regular expression instantly becomes more readable and more maintainable. Another example of Unicode property escapes is matching all math symbols according to the Unicode standard. This would match the not equals to sign, for example. And here's an example that combines multiple property escapes. This pattern matches any letter, including non-ASCII letters and whitespace characters, according to the Unicode standard. And indeed, if we apply it on a piece of text that is written in Greek, it matches. This regular expression feature is not just useful in JavaScript. It can be used in HTML as well. Input and text area elements have a pattern attribute that is used for client-side validation. Unicode property escapes work there as well. So when this HTML document loads, the input field gets a light green background because the pattern matches the input value. As soon as you enter any character that is not a letter or a space, the input state switches to invalid, and the background becomes pink. Unicode property escapes are already implemented in Chrome, Opera, Safari, and Node.js. But Babel can transpile the feature, so you can use it while still supporting all browsers.
Another new feature involves looking around in a regular expression. Lookarounds are assertions that match a string without consuming anything. JavaScript supports lookaheads in regular expression. This is not new. Positive lookahead ensures a pattern is followed by another pattern. So in this example, we're matching ASCII numbers, but only if they're followed by a space followed by the word $. So for the input string $42, the match contains the numeric part 42. And similarly, negative lookahead ensures a pattern is not followed by another pattern. In this example, we're matching ASCII numbers, but only if they're followed by something other than a space followed by the word $. So for the input string 42 rupees, the match only contains the numeric part 42. Lookaheads are not new in JavaScript. What's new is a very similar feature. Regular expression patterns now support look-behinds as well. Positive look-behind ensures a pattern is preceded by another pattern. In this example, we're matching ASCII numbers, but only if they're preceded by a $sign. So for the input string $42, the match contains the numeric part 42. And similarly, negative look-behind ensures a pattern is not followed by another pattern. Sorry, not preceded by another pattern. In this example, we're matching ASCII numbers, but only if they're preceded by something other than a $sign. So for the input string rupee42, the match contains the numeric part 42. Look-behinds are just as useful as look-aheads. Until recently, there was no built-in way of using look-behinds in JavaScript. A workaround I've seen developers use in the absence of look-behind support is to reverse a string and then apply a look-ahead instead. This indeed mimics the look-behind behavior, kind of, but it's overly complicated and confusing. Thanks to native support for look-behind, we no longer need ugly hacks like that. And look-behinds are already supported in Chrome, Opera, and Node.js.
One feature that's related to regular expressions is string match all. It's common to repeatedly apply the same regular expression on a string to get all the matches. And this is already possible by writing your own loop and keeping track of the match objects yourself. But it's a little bit annoying to do so. So string.prototype.matchAll simplifies this common scenario and allows you to more easily iterate over all the matches. The idea is that you just write a simple for-off loop, and string matchAll takes care of the rest for you. String matchAll is still being standardized, but we have an implementation behind the flag in V8 and Chrome but we won't ship it until some open spec issues are resolved. So expect this to come to a browser near you very soon.
Another new proposal avoids the creation of an unused binding for try-catch blocks. It's common to use try-catch blocks to catch exceptions and then handle them accordingly. But sometimes you don't really care about the exception object that is available in the catch block. Still, previously you had to bind the exception to a variable, otherwise you'd get a syntax error. Luckily, this binding is now optional. In cases where you don't need the exception object, you can now omit the parenthesis and the identifier following catch. The code now looks a little simpler. This small feature makes patterns that don't use the catch variable play nicely with linters that complain when there's an unused variable. The catch binding is already optional in Chrome, Firefox, Opera, Safari, and Node. For wider support, use Babel to transpile this feature.
Another new feature has to do with trimming. You may already know about the trim method on strings, which trims whitespace on both sides of the string. Now, there's also the trim start and trim end methods. These methods allow you to trim whitespace from only the start or the end of the string. A very small but very useful piece of new functionality. One-sided string trimming already works in Chrome, Firefox, Opera, Safari, and Node. But for wider support, the functionality can trivially be fulfilled, including by Babel.
Another new JavaScript feature is the finally method on the promise prototype. Let's say we want to implement a fetch and display function that takes a URL, loads some data from it, and then displays the result in a DOM element. Let's walk through the implementation together. First, we display a loading spinner in case the request we're about to kick off takes a while. Then we start the request. If the request fails, we end up in the promise's catch handler. We display an error message and hide the spinner. If not, we continue. We get the HTTP response body in text form. We then show the text in the DOM element that was passed into the function, and then hide the spinner. So if the request succeeds, we display the data. If something goes wrong, we display an error message instead. Either way, we had to call hide loading spinner. Until now, we had no choice but to duplicate this call in both the then and the catch handlers. But in modern JavaScript, we can do better thanks to promise prototype finally. Not only does this reduce code duplication, it also separates the success error handling from the cleanup phase more clearly. Pretty neat. In this particular example, when you have full control over the code, you can also use async await, which is my personal preference. You could wrap that up in a try-catch finally block. Promise prototype finally is still useful if you don't control the code surrounding the promise, or if you only have the promise object. Promise finally is currently supported in Chrome, Firefox, Opera, Safari, and Node. And this functionality can be polyfilled.
The next feature I want to talk about is called Object Rest and Spread. And I hear you all thinking, rest and spread, that's not new in JavaScript, right? Arrays have had this for years. And you're absolutely right. Here's how REST elements work with array elements. We're using array destructuring here, and we have an array of prime numbers. And we want to extract the first and second elements into their own variable. We then store all the remaining array elements into an array that we call rest. And here's array spread in action. I know the syntax looks exactly the same, but there are two different features technically. If it's on the left-hand side of an equal sign, then it's rest elements. If not, it's spread. Anyway, here we take the parts from the first example, and we put them back together into a copy of the original array. These two features allow you to rest or spread array elements. But JavaScript now offers rest and spread functionality for object properties as well. This example shows how rest properties come in handy when using object destructuring. We have a person object, and we extract the first name and last name properties into their own variables. We then store the remaining properties in an object that we call rest. Spreading objects is now possible in object literals too. So in this example, we use the destructured parts from before, and we put them back together into an equivalent object that is effectively a copy of the original person object that we started out with. Spreading properties offer a more elegant alternative to object assign in many situations. Shallow cloning an object is one example. This is already possible using object assign, but it's a little awkward because you have to pass in an empty new object. With spread properties, you can just perform the spread as part of the object literal itself. It's much more elegant, and it even offers greater optimization potential in JavaScript engines compared to object assign. Merging objects is another example. Once again, object assign can already do this, but if you forget to pass in a new empty object as the first argument, then you end up mutating the default settings object, which is probably not what you want. It's just a little awkward. So spread properties help here too. By using them, there is no way to accidentally mutate objects. On top of that, the code is very nice and elegant and easy to read. Object rest and spread properties are currently supported in Chrome, Firefox, Opera, Safari, and Node. And Babel supports transpiling this feature.
Recently, JavaScript introduced classes that built upon the prototypal object model of JavaScript. A bunch of new proposals evolved the declarative API of classes. Here's a simple class for an increasing counter. There's a constructor that creates an instance property count and sets its default value to 0. We use underscore to denote that count is a private property, but that's just a convention. The language doesn't enforce it. We also install a getter and an increment method on the prototype. The new class fields proposal introduces public instance fields in classes. So this moves the instance fields from the constructor to the class body. A constructor function is no longer required. This new class fields proposal also introduces private fields. Private fields enforce the encapsulation at the language level. Private fields cannot be accessed outside the class body. So instead of using underscore to denote a private property, we use the hash sign. This is another bleeding edge feature that is still being standardized. We have an implementation behind a flag in V8, and we're looking forward to shipping this soon once the spec issues are resolved.
So we've looked at a lot of cutting-edge JavaScript features today, but what's the main takeaway for developers? The JavaScript language is continuously evolving, and we're working on making new language features available in V8 and Chrome as soon as we can. Developers like yourself shouldn't be afraid to use these modern JavaScript features. They have decent baseline performance, and in many common cases, they're even faster than handwritten or transpiled equivalents. We understand that you do need to support a wide range of browsers and environment, and transpiling your code helps with that. But we ask you to consider transpiling selectively, to keep bundle size small, and to avoid transpiling away the potential optimizations that these modern language features hold. Babel preset env allows you to transpile only those features that you really need to transpile based on the browsers and environments that you support. Similarly, we recommend continuing to use existing bundlers, such as Webpack or Rollup. They work very well together with modern language features, especially with modules, and they help you provide a performance experience to your users. We're interested in your feedback on this presentation, so please go to this website and let us know what you think. And don't forget to follow us on Twitter and follow V8.js as well. We'll be tweeting links with more information about the features we just discussed. And after this talk, we'll be hanging out at the Web Sandbox, so just come over and talk to us if you have any feedback or questions at all. Thanks for listening, and enjoy the rest of I/O.